Hello, my name is Chanyeok Jung from the DTM lab at Dongguk University. Today I will be presenting a review of the paper titled A Systematic Way of Identifying and Forecasting Technological Reverse Salient Using QFD, Bibliometric and Trend Impact Analysis. This is the bibliographic information. The paper was published in Technovation in 2014 and its keyword and research objective are as follows. The table of contents is structured exactly the same as that of the original paper. This is the introduction. Emerging technologies are crucial for commercialization as they create new growth opportunities by restructuring industrial systems and competition rules through disruptive innovation. However, some emerging technologies often experience delay in commercialization compared to initial expectations. Many previous studies have pointed to factors such as financial resource, human capital, assertive capacity, and collaboration as key causes of commercialization delay. Yet it is important to identify technological obstacles in the early stage of development and non-technological factors in the late stage. Most existing research relies heavily on expert judgment, but the increasing complexity and certain life cycle of technologies have made such assessment less reliable. Bibliometric analysis has been proposed as an alternative, but it has limited applicability in real-world R&D decision-making. Therefore, this paper proposed a systematic methodology that utilizes the concept of reverse salience to define, identify, and prioritize technological obstacles and to forecast when those obstacles may be overcome based on performance criteria. This is the literature review section. Like the until review of technological system, the systematic perspective sees the technology system as being composed of multiple interacting subsystems. When a particular subsystem fails to deliver the required level of performance compared to other subsystems, a continuous lag due to interdependencies can hinder the overall progress of the technology and limit the system collective performance. Such underperforming subsystems can be defined as reverse salient. Research on forecasting RS is still in its very early stage, and to date there has been only one peer-reviewed study which applied a simple extrapolation method. Objective and structural identification of reverse salient can make the RS concept more useful and relevant for researcher technology developers and managers. However, experts have faced difficulties in providing reliable time-based forecast of RS performance. In this context, QFD is relatively free from such limitation as it effectively captures and translates user needs, making it suitable for RS identification. Among existing forecasting methods, trend impact analysis and causal impact analysis are capable of meeting this forecasting requirement. By combining QFD with TIA, the approach proposed in the study is expected to overcome the limitation of previous methods. This section provides the technological background of Shin biosensors. Nanobiosensors are devices used to detect small amounts of biomarkers such as specific genes of proteins. Among them, carbon nanotube biosensor exhibit excellent sensitivity and can operate without the need for additional markers or expensive optical sensing equipment, making them well suited for miniaturization. Despite the proposal of various scientific biosensors, none have been successfully commercialized. The main reason for this failure lies in unresolved technological liver salient. Therefore, in order to achieve the successful commercialization of scientific biosensor, it is essential to identify and resolve these technological areas as a top priority. This is the methodology section. Looking at the research methodology, the first step is identifying RS using QFD. In this step, the commercialization stage, core technologies, and key physical properties of CMT biosensor are defined. The second step is performance analysis and gap identifications. Using patent and paper data, the study analyzes performance trends over time and applying the liver salience framework to identify the current performance gap of key RS for commercializations. The final step involves future forecasting and performance gap trend analysis using TIA. Here, future performance is predicted using growth curve and period-based models, while expert opinion are incorporated to estimate the timing of RS resolution and to examine future trend in performance gap reductions. QFD was originally developed to reduce certain biases in expert judgment and to systematically identify reverse salient. Since it is considered both technical and market perspective, it is more suitable for technology commercialization research compared to other methods. Bibliometrics is defined as the quantitative study of publication reflected in bibliographic data. By analyzing large-scale global bibliometrics dataset, it becomes possible to reduce the subjective and regional biases often observed in expert-based evaluations. However, bibliometric indicators alone are not sufficient for making concrete R&D decision in practice. Considering this, the study combines QFD and bibliometric, leveraging the strengths of both methods to minimize the biases inherent in expert judgment. TIA is a forecasting method designed to adjust time series by incorporating perception of how future events may alter baseline projections. It consists of two main steps. First, fitting a trend based on historical data. Second, modifying that trend based on estimated probability and impact of future events. Because TIA can account for future uncertainty while avoiding the risk of simple extrapolation, it is considered more suited for forecasting the future performance of RS. In addition, various expert-based methods such as Delphi, scenario analysis, roadmap, and MCDM have been used for RS identification and forecasting. However, these approaches often suffer from limitations such as subjective bias, inconsistency among experts, and negative effect of group dynamics. In this context, QFD not only reduce such biases, but also meet methodological requirements for structured and proactive identifications, while incorporating a balanced perspective on both technological and market factors. This section presents the empirical analysis and result. First, a panel of 6 experts participated in identifying and prioritizing the reverse salient that hinder the commercialization of CMT biosensors. For biometric analysis, a total of 7,439 patents and 42,000 academic papers are collected from the USPTO and Web of Science database using keywords such as CNT, SWCNT, and other related terms. Next, based on a review of the 42,000 papers from major commercialization stage were divided: mission research, production technology development, application technology development, and commercialization technology development. Through literature review, 7 core CNT biosensor technologies were selected and expert discussions were conducted to identify the key technology associated with each commercialization stage. As a result, the synthesis of high-purity SWCNTs was identified as the highest priority RS. In addition, the expert feature classified the selected technologies into 6 sub-technologies, ultimately identifying a total of 13 core technologies. Through a combination of literature review and structured brainstorming, 9 market demands were developed and categorized into 4 evaluation dimensions: performance, usability, economic feasibility, and regulations. Using a QFD matrix, the relationship between market demand and technologies were evaluation on a 139 square, and the priority of Rs was determined based on the weighted scores. As a result, A4C and A4D were identified as key Rs with both high difficulty and high importance, and thus must be addressed as top priority issues in the CNT production technology development stage. Next, the KPIs for A4C and A4D were defined by combining literature review with expert judgment. Using the previously collected patent and paper dataset, KPI-related keywords were used as queries, resulting in the retrieval of 95 USPTO patents and 18 journal articles from the Web of Science database. An analysis was conducted on A4C, the pretty of semiconducting establishments. Patent and journal data were used to graph the 3-year moving average of the KPI between 2000 and 2011. As shown in the graph, the pretty of semiconducting establishment increased from 82% in 2004 and stabilized around 95% by 2008. Since most biosensor markets require a minimum purity of 95%, this indicates that the RS issue related to A4C was largely resolved by 2008. Additionally, a logistic curve was fit to the 3-year moving average date to predict the year when 99% purity would be researched. However, in contrast to the forecast, the purity level did not improve future after 2008. To understand why the purity did not continue to increase, a graph was generated showing the 3-year moving average of the annual number of patent and journal articles that include semiconducting establishment purity information. The research showed that the number of journal articles peaked around 2004 and then steadily declined, while the number of patents peaked in 2006, displaying a similar pattern. This suggests that basic scientific research reached its limit in 2004 and applied research hit the performance ceiling in 2006, after which both entered a period of stagnation with minimal technological innovation. A qualitative review of recent publication feature confirmed that no new separation technologies have been developed since the centrifugation method introduced in 2005. Therefore, it is expected that the purity of semiconductor establishments will not exceed 95% in the near future, and this level will likely remain the standard for scientific biosensor intended for implantable medical applications. Next, an analysis was conducted on A4D, the large-scale separation capacity of SWCNT. A bibliometric analysis was used to visualize change in standard performance between 2004 and 2011. The results showed that until 2004, the separation capacity ranged between 1 mg and 10 mg, but it increased rapidly and reached approximately 150 mg by 2011. However, the minimum separation capacity required for commercialization is around 10,000 mg. In the early stage of performance improvement, various future uncertainties can affect the achievable separation scale. Therefore, trend impact analysis was applied to incorporate major future uncertainties and adjust the projected performance trend using historical performance data from 2004, 2011, and exponential curve was applied to extrapolate and forecast the performance up to 2020. In other six sports identify major future events that could alter the performance curve and assess both the probability and impact of this event through 2020. As shown in Table 7, the values were finalized collectively through group discussion, while the expert expressed confidence in future advancement in CNT technologies such as improvement in separation method and production technique. They also pointed out two external risk factors: the emergence of competing nanomaterials for biosensor application, a decline in R&D investment in CNT technologies. Next, the Monte Carlo simulation was conducted to forecast the future performance of A4D. This simulation is based on the assumption that is a randomly generated number exceeds the assigned probability from a given year. The corresponding future event is considered to occur in that year. The total impact of all occurring events is then accumulated and applied to the projected performance curve for their year. This process was repeated 500 times with each iteration representing a unique mini scenario. By generating over 100 scenarios, the study was able to estimate a broad range of possible future outcomes, including key statistical indicators such as the 5th and 95th percentiles. The following present the forecast performance results for A4D. As shown in the figure, future events generate a asymmetrical range of uncertainty that shift the median estimate future away from the original extrapolate baseline. If a large number of positive events occur, technological performance may improve rapidly, allowing the market required level of 10 grams to be reached by 2017. However, if more negative events occur, there is a possibility that the required level will not be achieved even by 2020. As a result, A4D exhibit a significant performance gap, and it is expected that these are RS will not be resolved before 2017. Furthermore, the separation scale of semiconducting SWCNT remains the greatest technical bottleneck to the commercialization of CNT biosensor, and thus innovation efforts should be concentrated on overcoming this RS. This is the conclusion. This study offers contribution from both practical and academic perspectives. From a practical standpoint, the proposed method help campaigns identify current and future core technologies, optimize their R&D portfolio, and enhance productivity. By combining QFD with bibliometric analysis, the approach facilitates consensus among internal experts, define and quantifies R&D KPI, and enable global performance monitoring. In addition, TIA supports forecasting by quantifying major uncertainties and events, thus helping to estimate when key technological bottlenecks may be overcome. From an academic perspective, this study presents a systematic methodology for the early identification and prioritization of RSS and provide a framework for forecasting future RS performance range based on KPI-driven performance gap analysis. However, the study also has several limitations. First, since market requirements rely on expert judgment, some internal technical driver may be overlooked. Second, TIA has limited applicability to forecasting disruptive or short-lived technologies. Lastly, the overall process is time and labor-intensive, indicating the need for greater efficiency through the use of information and communication technologies. This concludes my presentation of the paper. Thank you.